This video is the second part of section 6.2, where I'm going to show you an example of finding the area of the region between two curves. And this example is actually a compound example, and I will talk more about why that is in a little bit. So first of all, let's look at the given information. We want to find the area of the region that's bounded by these two curves. Now, I'm going to draw the two curves so I can see what my region looks like. And the more accurate you are with your graphs, the better. So if you actually have graph paper, even better. Let me start off with graphing g of x equals the absolute value of 2x. So I know absolute value functions are v's, and because it has a multiplier, a scalar multiple of 2, it's going to look something like this. Can't tell you how much easier it becomes if your graphs are accurate. Let's look at graphing negative x squared plus 3x plus 6. So first of all, I know it's quadratic, and because of the negative, I know that it's reflected upside down. But it might be helpful to find some intercepts in order to graph this more precisely. I know that it has a y-intercept at 6. If I set the thing equal to 0, I can find its x-intercepts. And so its x-intercepts, if I divide everything by -1, will make it easier for me to factor. And so let's see, factoring this, looks like I don't have any whole number factors that actually make this work. So let me take a guess, and we'll deal with that later. Okay, so no easy way to graph using your x-intercepts. But that's okay. The region bounded by those two curves is this region here. And one of the things that's super important for us to figure out is the interval over which we are going to be integrating. And that interval is not provided for us, but you can see here that it's bounded on the left and the right by the points of intersection of the two graphs. So what we do need to find are those points of intersection, or at least the x values of those points of intersection. So I would recommend pausing the video right now, and let's see if you know how to find that. We want to find out where these two functions intersect. And we're back to take a look at the points of intersection. So in order to find those, we could set the two functions equal to each other. And so we've got the quadratic function equaling the absolute value of 2x, which we would need to set up in split up into 2x and negative 2x. And so remember, solving these, you'll want to get all of the like terms on one side, setting the whole thing equal to 0, and then you'll want to either factor or use the quadratic formula in order to solve. So for each equation that we set up, we actually get two possible answers, x equals 3 or x equals -2, when we set it equal to the right side of the function, the positive side of the function. And then when we set it equal to -2x, the other side, we get either 6 or -1 for our solutions for x. And if we take a look at what the graphing calculator gives us as far as a graph, we can see that they actually do intersect at x equals 3 over here on the right side, and on the left side x equals -1. So we can use some other algebra to figure that out, but just to save a little bit of time, we've got positive 3 and -1. So that is actually our interval. That represents this area here bounded by those two curves. All right, so now let's actually find the area. Well, you'll notice a few minutes ago that when we went to find the points of intersection between these two curves, that we had to take the absolute value of 2x and split it up. And that is the reason that this is actually a compound example, where we actually need to use two intervals of integration. So we need to set up two different integration pieces over two different intervals, and we need to add them together. And the reason is that we can't integrate the absolute value of 2x, but we can integrate each of the components that make up the absolute value graph. We can integrate 2x and we can integrate negative 2x. So that's what we're going to do. So if we look at, by the way that I have this drawn, it looks like it's symmetric, and I'll just tell you that it's not. It's just because of my sloppy graphing. If we go back to the graphing calculator, you can see that the two regions are not symmetric. The region on the right side of the y-axis is much larger than the region on the left side of the x-axis. And that's where finding the x-intercepts of the function may have been more helpful. And now that I look at it, I'm wondering if I just didn't take enough time to figure out what those factors would be, because it kind of looks like it does go through at whole number values. But at any rate, those values aren't going to help us. Okay, so I need to set up two integrals. And so one of those integrals is going to incorporate the left side of the y-axis, and then the other is going to incorporate the right side. Okay, so interval-wise, on the left side, this point of intersection is at -1. And so from -1 to 0, that is the area, or that is the interval of the area on the left side. And then on the right side, I'm going from 0 to this point of intersection, which is at 3. So from 0 to 3. Remember the formula. I need to take the top curve and subtract the lower curve. So I'm going to take negative x squared plus 3x plus 6, and I'm going to subtract negative 2x. I'm on the left side of the x-axis, and so in the absolute value graph, that's negative 2x. Put my plus sign a little too early there, had to squeeze all of that in. Over here, I'm going to take the top curve. So I'm going to take this orange curve right here, and I'm going to subtract the green curve. And so from that one, it's going to be just subtracting positive 2x. So watch your signs here. In this one, I'm subtracting negative 2x, which becomes a plus, and this one I'm subtracting positive 2x, which stays as a negative. So we will actually get two different functions when we combine like terms. So on the left side of the x-axis, we have negative x squared plus 3x plus 6 plus 2x. It's not absolutely necessary that you combine those like terms, but I think it just makes things cleaner. Less room for error there. So negative x squared plus 5x plus 6. And then with the other side, negative x squared, we have a positive 3x and a negative 2x, so that's plus x plus 6. Okay, so what we need to do is we need to find the antiderivative of each of these functions, and we need to use the fundamental theorem of calculus to utilize the intervals and calculate the area of each region. So once again, let's pause the video and have you try some of that manipulation, and we'll come back and we'll check answers. We're back to take a look at the final answer for this problem, and you'll see that I got 50 over 3. So if you got that, great job. You can go ahead and skip over this explanation. If you need the explanation, go ahead and listen. So finding the antiderivative of each of these pieces, I have negative x cubed over 3 plus 5x squared over 2 plus 6x. And so what I need to do is substitute 0 into all of that, and then substitute negative 1 and subtract those results. So obviously if I plug 0 into every term, I'm just going to get 0. But don't skip over that, because you do have to subtract the next piece, and so it is going to change its sign. Now, sometimes I use my graphing calculator to help me with some of this. It is something you have to know how to do on your own, so when it comes to an exam, you'll have to do all the tedious fraction work, but sometimes I just get tired of doing it again and again, and I want to save some time. So what I want to do is take negative 1 cubed plus 5 halves times negative 1 squared plus 6 times negative 1. And I want it to be given in a fraction. So what I get for that particular piece is negative 5 halves. And it looks like when I double check my notes, I get 19/6. So, oh, I see. Sorry. I forgot to divide it by 3. So let me try that again. So negative 1/3 times negative 1 cubed plus 5 halves times negative 1 squared plus 6 times negative 1. And again, I would like my answer in a fraction. So negative 19/6. So this is something I could do by hand. I'm just trying to show you how to check your work, essentially. And so if I subtract negative 19/6, I get positive 19/6 for that piece. So over here, I need to do my antiderivative again, and I'll get some different terms here. And then I need to plug in 3 and 0 and subtract them. So let's take a look at what happens when I plug 3 into that antiderivative. So negative 1/3 times 3 cubed plus 1/2 times 3 squared plus 6 times 3. I want it in a fraction, and that gives me 27 halves. When I plug 0 into this function, it's going to give me 0. So I'll get 27 halves minus 0, which is 27 halves. So I've got the area of the left side here. This region is 19/6, and then this region here is 27 halves. Again, they're not symmetric, even though it looks like it in my drawing. And so let's add the two together, which I could do by hand if I felt like it. I just want to keep reiterating that because I don't want you to rely too much on your calculators. But sometimes if you're getting your answer wrong, it could be because of your fraction work, which is kind of disappointing since you're doing all this great calculus. But 50 thirds is the final answer there.